Hi, everyone. Welcome to Lecture 5 for the Modern Machine Learning Simple Methods That Work course. And in this lecture, we're finally going to get to one of the main results of the course, which is this connection between training infinitely wide neural networks and solving kernel regression with a specific kernel called the neural tangent kernel. And we'll see that these two things are equivalent. And this is a very powerful message because now we've connected a very simple class of models, kernel methods, which are very easy and simple to implement in a few lines of code, with a very large class of models, neural networks. So we should hopefully be getting the flexibility of neural networks and combining that with the simplicity of kernels to produce a very powerful set of methods. So before we dive into this exact connection, I just want to review a bit what we did in the last few lectures. So remember, we had built up this whole foundation of linear regression and kernel regression. And in particular, what we did in the last lecture is introduced something called the neural network Gaussian process. And this, I denoted the NNGP. And this was our first connection between kernels and training the last layer of very, very large, infinitely wide neural networks. So this one connected, training just the last layer of wide neural networks with solving kernel regression. And in particular, remember we had neural networks, which were these maps from RD to R. And I considered the case of just a one hidden layer neural network, which was parameterized by two weight matrices, A and B. And I had some element-wise activation. So here I wrote A is a R1 by K matrix. B is a RK by D matrix, and phi was some element-wise activation. And common examples were this ReLU or sigmoid or any of the other ones you would have seen in practice for neural networks. And in this setting, what we did, and I'll draw it in blue here, is we just thought of the matrix B as initialized with some random values, B naught, and just frozen. So when we trained, when we solved, when we minimized this square loss with gradient descent for neural networks, we would only ever update the parameter A. And remember that given a set of data points, xi, yi, which was our training data, we would minimize this mean squared error, which here I would just denote as a function of A because B was not being trained. And this was just the sum, I equals 1 to n, yi minus A phi of B naught xi squared. And so we would start gradient descent, which I'm denoting GD. And this we would just start with A naught equals 0 and solve linear regression. This is just now a linear regression problem with my features transformed by this feature map, which took every xi and mapped it to phi of B naught xi. And remember that this introduced, anytime we have a feature map like this, we can write it in terms of a kernel. And so the corresponding kernel, which I'll actually denote by sigma, was just this inner product phi of B naught x, phi of B naught x tilde. And these were vectors in RK. And so remember the next question that we had in mind was we could do this for any finite value of k. There's nothing different from what we were doing with linear regression and kernel regression. when k is finite. But the good part about kernel regression is that we can actually understand infinite dimensional feature maps. So these are maps into an infinite dimensional or Hilbert space. And so to handle this, to compute this kernel when k was going to infinity, remember we just added this scaling factor, 1 over root k. And out here we would have a 1 over k, and this let us use the law of large numbers. As k went to infinity. And this we denoted as the neural network Gaussian process. So this kernel here, so this sigma xx tilde, we just took limit as k to infinity, 1 over k of phi of b naught x and phi of b naught x tilde. And we computed this. And remember that when our data, so when x and x tilde were on this sphere in d dimensions, so this is this condition that the norms of x and x tilde were just 1, we would use something called the dual activation and just very simply write our neural network Gaussian process in terms of the dual activation. And so this here was called the dual activation. Okay. So the reason I'm recalling all of these facts is because all of these forms, including this connection with the dual activation, are going to come in incredibly handy when we actually compute the neural tangent kernel. But before I introduce what the neural tangent kernel is, right now, and thus far in this course, we've always thought of neural networks as maps on data. So even when I wrote this here, I'm technically considering the neural network as a map where I feed in some data in RD, and I'm getting a real valued output. And this is a really useful parameterization of this neural network, or useful description of the neural network when we're trying to implement it. In implementation, we usually feed in some data and expect an output. But for understanding this connection with kernels, and especially understanding optimization for neural networks, it actually helps to think about neural networks as a map on both data and parameters. And in fact, this map on parameters is what we're going to emphasize today. So typically, we think of neural networks as these maps from RD to R, and assuming you have some parameters, we just implicitly assume those parameters are fixed and write it in this form. But now the thing is that for training, the parameters are the thing that are being updated. The data is somehow fixed. If I think about one data point and I want to minimize square loss, this data point is unchanging, and I have just a map from parameters to real values. And so instead, what we're going to do, more generally, neural networks are actually these maps on both parameters and data. So I'm going to write it as RP cross RD to R, where f of x, so instead of f of x, I'm going to write it as f of w semicolon x. And this is just a phi of bx again. Nothing has changed. It's still the same neural network. So this is so far just a pedantic notation change. But here what I'm going to do is I'm going to call my w. This is going to be a giant vector of all the parameters in A and B. So I'll have A11, A12, A13, all the way up to A1K. And then I'll have B11, B12, up to B1D, B21 up to B2D, and then all my parameters up to BKD. And here recall that A is a 1 by K matrix, and B is a K by D matrix. So W should be an R K plus KD. It's a giant vector, And I'll write a transpose here so that it's a column vector. And it's a giant vector that has k plus kd dimensions. Okay. So why is this now useful? Well, one simple trick that we can do, remember that gradient descent always starts with some initialization, W naught, and then updates the parameters via these iterative steps. So the question is, maybe I want to approximate the neural network with a very simple linear approximation. And to do this, what I would do is in this new setting, I can actually just fix the data x and take a first order Taylor series expansion around this initial point W naught. And recall what this is. So what am I going to do? So now fix any data point x. So I'm going to write my neural network in this form, where x is now a subscript, and w are really the parameters that are changing. So it's a map on these parameters. And I'm going to typically write this as rp into r, but of course here we know that p equals k plus kd in this example. Okay, and so how do I write my Taylor series expansion? Well, just remember that if I was to do a first order expansion, this will just be, I'm going to denote it as fx tilde of w. And this is just the initial value at some w naught plus the gradient at w naught transpose times w minus w naught. And this is exactly what you would have seen. So this is my, so in red here, this is just a first order Taylor series approximation of fx at w. And I'm going to call this a linearization. So this will be my linearization of the neural network around some initialization w naught. Okay. And just remember that if everything is in 1D, so if we only have one parameter, so if p equals 1, remember that this just looks like the following. This just looks like fx at w naught, f prime of w naught, w minus w naught. This is exactly what you would have seen in a multivariable in calculus 1 or 2. We're just doing it in the multivariable setting, just up to the first order term. So now, why is this useful? Well, remember that if we have a linear model here, when we just update, we have now a linear model in W. And so if we're updating the parameters W via gradient descent, this is again just solving linear regression. And in fact, there's some extra terms here which look a bit confusing. And for now, let's just ignore these. And in particular, let's just ignore the two terms here. What does this look like? Well, we are now using a model where, and let me write this in blue because it's not an exact model. Let's just say for now, f tilde of x at w is just the following. Well, this actually just looks like inner product between between w and gradient fx at w naught. And so if I was to solve, if I was to substitute this into my square loss, instead of substituting in f of wx, what I would see is that my square loss, which remember before was the summation I equals 1 to n yi minus f of xi squared, we're now approximating this by the following. summation I equals 1 to n, yi minus inner product w gradient of f of x at w naught squared. And here in the denominator, in the subscript here, we have an xi. That's where our examples are coming in. But now this should look extremely familiar. And in fact, what we see is that this term is just this whole loss. We now built a linear model on top of some transformed data. And that transformation, that feature map, is exactly given by each xi mapping to this gradient. Gradient f of xi, w naught. And so what can we do is we can, whenever we have a feature map like this, we can use kernel regression, and we can define an associated kernel. And this kernel between any two examples, x and x tilde, remember, is just the inner product of psi of x and psi of x tilde. And now, using this notation on the left here, we just have that this is gradient f of x of w naught, gradient f of x tilde at w naught. And this whole term here is called the neural tangent kernel, or NTK. And I'm going to rewrite this because a lot of steps have happened here. I want to rewrite this in the next page. And recall that there's a few things that we did here that didn't seem so formal, which was that we were ignoring this term w naught and ignoring this predictions at initialization, this constant term in the linearization. And in fact, we'll get back to this as a point later, but I just want to write out a clean definition of this neural tangent kernel. And since everything is so abstract here, I want to give a concrete example of a one hidden layer neural network and its corresponding neural tangent kernel. And note that so far, we haven't done anything where we've considered infinite width networks or anything like that. Just as we did for the neural network Gaussian process, we're just writing some approximation of a neural network, of any finite width neural network, and just noticing that this linearization that we wrote out corresponds to training a linear model on transformed features, which is just kernel regression. And so we just computed what the kernel induced by this feature map is, and that is what we're defining as the NTK. And what we'll do next, after we go through some examples of what the NTK looks like for a finite width network, we'll again use our same law of large numbers trick and evaluate what this NTK is for an infinite width network. So let's just cleanly write out the definition. Okay. So let f I'm going to consider for any data point x a function be a neural network on parameters, p parameters to real values r. So I'm going to say this is a neural network. Okay. The neural tangent kernel for f of x, for f here, is given by k of x, x tilde, which is just this gradient. Here where w naught is an initial, value for parameters. Okay. So now let's just go through a quick example of what this looks like. So let's just say I have f, which I'm going to consider a neural network I'm going to write it as in this general notation, f of wx. And for real valued x, so here I'm going to consider my x in real values. I'm just going to write it, actually I'll consider it in d dimensions here. I'm just going to write it as a phi of bx, just as we did before. And here my a is going to be a 1 by k vector, b is going to be a k by d vector. Okay, and then of course phi is this element-wise activation. And now I'm actually just going to simplify this a bit further. I'm going to write it as the sum I equals 1 to k of a1i phi of bi colon x. And why is this the case? Remember that this bi colon terms here, these are just the ith row of b. And because my a is just a row vector, if you just expand out the terms in a of phi bx, you'll see that it has exactly this form. And we did this computation in the last lecture for the neural network Gaussian process. So now what I need to do is compute these gradient vectors up here for any two examples, x and x tilde. And so how do I do this? Well, let's just take some example x, f of x of w naught. So what is this? Well, remember that the gradient is just a vector of partial derivatives. In this case, it's going to be partial derivatives with respect to every parameter. So this is just going to be partial of f with respect to a11, partial f with respect to a12, all the way up to partial f of x with respect to a1k. And then we have to do the same thing for the b's. So partial f with respect to b11, all the way up to partial f with respect to bkd. And I'm putting this transpose here just to make sure that all my gradients are column vectors. Okay. Now let's just go ahead and compute these. So for any I, what is partial f of a1i? Well, this is just phi of bi colon x. And similarly, and this is all, remember, this is all coming from this formulation here. This makes it a lot easier for me to see because I just look at the a1i term, and then I can pick out that the partial derivative is phi of b1i. The phi of I colon x, I mean. And now if I do partial f of x of partial b, let's call it ij, well, this is just going to be a1i. It has to correspond to the a1i term because I have an I in bij. Then I take phi prime of I colon x. And now via the chain rule, I just have to take the xjth coordinate here. So this would be the jth coordinate of x. Okay. And so now what I need to do is just exactly compute up here this inner product for any two examples, x and x tilde. And so let's just do that. So k of x, x tilde. If I write out what this inner product is in terms of a sum of these partial products of partial derivatives, this is just exactly, if I group all the a terms together, this is just a sum from I equals 1 to k of partial fx, partial a1i, and partial fx tilde, partial a1i. And then I have a sum over all of my b parameters. Remember, there's kd of them. So I have to have two sums, one from 1 to k, one from 1 to d. And these are just going to be a1i times a1i phi prime of bi colon x, phi prime of bi colon x tilde, xj, x tilde j. And now I can do some simplifications here. Remember, here I have a1i, a1i. This is just going to come together and be an a1i squared. And then I want to just write this cleanly on one line. So I can just move these over and similarly just move these up. Okay. And now you see here, there's a couple of things that have already appeared. Well, here, my partial fx of a1i times partial fx tilde of a1i, this is just going to be phi of bi colon x, phi of bi colon x tilde. And now this should look very familiar. If you followed along in the last lecture, there should be some terms here that look a bit familiar. And what I'll do is I'll circle this one here in red. And this part here, I want to rewrite a bit cleaner. You see that only these xj and xj tildes actually depend on the index j. Nothing else in that summand actually depends on j. So I can actually regroup those terms and write it as sum from I equals 1 to k, a1i squared, phi prime, bi colon x, phi prime, bi colon x tilde. And now sum from j equals 1 to d, xj, x tilde j. This here is actually just the term x transpose x tilde. And so if I reduce this even further, we'll see that this here is just sum from I equals 1 to k, a1i squared, phi prime, bi colon x, phi prime, bi colon x tilde, x transpose x tilde. And I'm going to circle this term in blue here. Okay. So now this first term in red, this should look very familiar. In fact, we're seeing that we're missing the scaling factor of 1 over k in front. But if we had that, this would exactly be the neural network Gaussian process. And now the term on the right, this looks a little bit different, but you again see you have this product of phi prime and phi prime. This will again be another neural network Gaussian process corresponding to a neural network which has the activation function phi prime. And so whatever theory that we used in the previous lecture, this is exactly what we will use to compute the neural tangent kernel in this lecture. Okay. But this is just a simple computation of I'm just writing down all the partial derivatives and what this neural tangent kernel actually looks like. So let's just now do this calculation again, where we introduce these 1 over k terms and see what we get. So now, consider a one hidden layer network F, but instead of having a phi of bx, I'm going to now consider a times 1 over root k phi of bx. Just like we did for the neural network Gaussian process, this 1 over k is coming in so that we can apply something like the law of large numbers. And now, if these a1i, and so here, again, I'll just write it out for completeness, but a is a r by k row vector, b is a k by d matrix. Now, if the a1i and the bij are IID drawn from a standard normal distribution, and for this is for I in the set 1 through k, j in the set 1 through d, then sorry, and let's assume, and we have data, on the unit sphere. So this means that norm of x tilde equals 1. Then the neural tangent kernel is given by k of x tilde, which is just the dual activation of x transpose x tilde plus the derivative of the dual times x transpose x tilde. And this is where phi hat is the dual activation of phi. Okay. And this will be our, let me do this here. This will be our first theorem in this lecture. Okay, so we've basically done the proof, but let's just write it out carefully again. So following the previous computation, what you should be able to see is that k of x tilde, remember it's just this inner product with respect to these initialization values, w naught. And before, if I just look at the previous page, now in this inner product, I'm just introducing this extra 1 over root k term here. Oops. There'll be an extra 1 over root k term here and here, which will come out as a 1 over k on the outside. And so we'll just have to multiply whatever we had before by 1 over k. And so we'll exactly get this term in red and blue, just as from before. And this is just going to be this term in red, which is just phi of bi colon x, phi of bi colon x tilde, plus my term in blue, which remember, I had just written as a1i squared phi of bi colon x. This is a phi prime bi colon x tilde, and an x transpose x tilde. So things are starting to look already a bit good, because remember from the last lecture, this is exactly the neural network Gaussian process. So because this is the NNGP, this part is exactly phi hat of x transpose x tilde. So that's good. Now here, we already have the x transpose x tilde term. So all we need to do is prove that 1 over k I equals 1 to k a1i squared phi prime of bi colon x phi prime of bi colon x tilde. We need to prove that this equals the dual activation derivative of x transpose x tilde. Well, now this actually is not too bad still, and the reason is that if we look at that term in blue, so let's say I call this, let's say I call this part here S. So what happens is limit as k goes to infinity of S. This is just going to be an expectation over, I'll call it now A and B, A and W, sorry. And this is by the law of large numbers. This converges in probability. S converges in probability. Maybe I'll call it an SK. And this will converge in probability to this expectation of A squared phi prime of W transpose X, phi prime of W transpose X tilde. And then here, this A is distributed like a standard normal. And this W is just an isotropic Gaussian. So this is a vector. So this thing is a vector in RD. Okay, but now the key thing that we assumed, remember, is that these AIs and A1Is and BIJs are IID Gaussian variables. So that means this A and W are actually independent. And so when you have an expectation of a product of independent variables, random variables, you can just separate it into the product of their expectations. And now remember the expectation of A squared is just 1. So this is going to be A squared expectation of phi prime W transpose X, phi prime W transpose X tilde. So this part is just 1. Now this is exactly what we saw from before. It's another neural network Gaussian process, but now with just the derivative of phi instead of phi. So this is the neural network Gaussian process of this network with activation phi prime. But remember, when you have the dual activation, this was the key property I mentioned in the last lecture. The dual of phi prime is exactly the derivative of the dual of phi. And this is the dual commutes with differentiation. And so this is exactly phi checkmark derivative of X transpose X tilde. And then we're done. So putting it all together, we now know that this part in blue, don't forget the X transpose X tilde that's outside there, this is exactly the term that we wanted. And so this will conclude the proof. And so now we've established a nice closed form for the NTK. And there's a couple of key things that I wanted to mention here. And the first one is that we see that when the data is on this, we did this for all when data is on the sphere. There is a similar formula you can do for the NTK in general. I didn't want to write it out in great detail in the course because I find the dual activation notation much easier to understand, and it avoids some unnecessary cluttering of notation. But of course, in the homework, I'll give an example where this formula can be easily extended for ReLU activations to general data. The second comment I wanted to make is that note that all of the expectations that we had worked with so far, we didn't have to do any new derivations of expectations, and all the hard work was just done in the previous lecture once we knew the neural network Gaussian process. And so all we need to know to compute the NTK of a fully connected network is just the dual activation. And so if we know the dual, we can take the appropriate derivatives and just write the NTK. So there's no extra information really that's needed to compute the NTK if you already know the neural network Gaussian process. And this actually is kind of a remarkable fact. And what we'll see in the following lecture is that, in fact, if you just know the dual activation, so just the NNGP of a one hidden layer fully connected network, you're actually good to go to compute the NTK of any deep network, of any deep fully connected network. And we'll see that this comes about very nicely from just the same sort of computation, although it's just slightly more involved in this deep network case. Okay, so now what I want to do is just give a simple example of how to actually write out the NTK for a ReLU network. So remember in the last lecture, we gave the example for the neural network Gaussian process for a ReLU network. So let's see, let f of x, let's let it be root 2 over root k, phi of bx. And here phi is going to be the ReLU activation, which is just max of 0z. And the reason I'm writing this root 2, this seems mysterious at first, but the reason that this appears here, and actually in a lot of the literature, is because when you have the root 2 there, the dual activation is normalized so that phi, a check mark of 1 is 1. And this is, I'll do this calculation here now as well. It's not too bad to see. But first, let's just remember that the dual activation in this case, remember that the dual in general is a function from -1 to 1 to real values. And here, the NNGP is given by sigma of x tilde, which is just for any data. Let's also consider this data x. Let's restrict our neural network to the sphere. It was just given by this x transpose x tilde. And this, we had a closed form for. It looked a bit messy, but it was just 1 over pi. I'm going to shorthand this inner product as psi. This is just going to be psi of pi minus cosine inverse of psi plus square root of 1 minus psi squared. Okay. So now we can ask, what is the NTK? K of x tilde. Well, remember that this, from the last slide, is just the NNGP plus x transpose x tilde times the derivative of the dual at x transpose x tilde. So now we need to just compute what is this derivative of the dual. So this derivative, this is just like we would have done in Calc 1 or 2. So this, I'm going to use the chain rule to expand out this part. So I can write it as the derivative of psi, which is just 1, times pi minus cosine inverse of psi, plus now the derivative of pi minus cosine inverse of psi. And the derivative of cosine inverse, so I'll just write here, because this is usually a tricky one to remember. This is just -1 over 1 minus psi squared. So we'll have a negative and a negative. Those will cancel out. And so we'll get plus psi over square root 1 minus psi squared. And then lastly, we'll have plus the derivative of square root of 1 minus psi squared, which remember is 2, square root of 1 minus psi squared on the denominator, and then a -2 psi on the numerator. Well, the 2's cancel out, and you see that these two terms also are equivalent, so they will also cancel. And we get exactly 1 over pi minus cosine inverse of psi. Great, so now we have all of the ingredients that we need to plug into this formula here. And so the NTK is just very simply given as, again, it's one of these things where the formula looks very complicated. But remember that this is just a one-time formula. We just implement it like you would the Gaussian kernel, and then you use it to solve kernel regression. And that's it. So this is the NTK for a ReLU network on the sphere. And notice that I added in that root 2 there so that the dual was normalized to be 1. So let's just actually check this. and I'll maybe call this y the root 2. So first of all, check that phi of 1, the dual of phi at 1, well, this is just 1 over pi times pi minus cosine inverse of 1 plus square root of 1 minus 1 squared. Cosine inverse of 1 is just 0. This whole part is just 0. So this is exactly 1. And now where is this root 2 coming from? Remember that the dual is actually this double integral over some expectation. But when you have the value 1 put into this, it just becomes, so phi hat at 1, remember, is just 1 over root 2 pi integral of phi at x squared e power negative x squared over 2 dx. So now we want this to be 1. Remember, phi now is the ReLU activation. So this is just square root 1 over 2 pi integral from 0 to infinity x squared e power negative x squared over 2 dx. And sorry, this is phi at 1 squared. It should be the norm of phi at 1, of the dual squared. And so this is actually just 1/2. And so if we want phi hat at 1 to be 1, we should have initially multiplied phi of x by root 2. So instead, if we had taken phi of x root 2, then you see we would have an extra 2 everywhere, and we would get a 1. And so this is exactly the computation for computing these appropriate scaling factors here, and this is where this root 2 is coming from. Okay, so now what have we done? We've done a lot of stuff in this lecture so far, but the important thing is we've derived, let me recap here. So this is just a brief recap. So 1, we introduced linearizations of neural networks. We used the linearization to derive the NTK. We saw that the NTK was just a kernel coming from this linearization. And 3, we calculated an explicit form for the NTK. This is all great, but it doesn't actually tell us that training neural networks is equivalent to using kernel regression with the NTK. We actually haven't made that connection yet. So what is the connection between neural nets and the NTK? And so this is the remarkable aspect of this. And unfortunately, a lot of the details of this theorem are out of the scope for this course. But what I wanted to do is at least present this theorem and at least highlight the intuitive steps that are necessary for proving this. And for those of you who are interested in the details, I have some references to papers in the notes. But the intuition is actually very simple, and that's what I wanted to convey in this lecture. So here's the statement. Training, and I always write it under certain conditions. So under certain conditions. And in fact, you now know what these conditions are. It's just the initialization according to this NTK initialization, which is just the IID standard normal for the parameters and this extra 1 over root k scaling. As network width goes to infinity, training neural network is equivalent to solving kernel regression, and I should say training a neural network with GD, gradient descent, is equivalent to solving kernel regression with the NTK. So this is an equivalence that actually holds as the width goes to infinity. But the best part about this statement is that because of this idea of the benefit of overparameterization, we expect infinitely wide or larger and larger models to do better and better on the data. So things have kind of lined up for us. And so we have that the NTK should be a very strong baseline for many, many machine learning applications. Okay. So how does one go about proving this? Well, the idea is actually pretty simple. So remember, actually, I'll write it as this. So our goal, show that a neural network is very close to its linearization through training. So if we were able to do this, remember that the NTK is solving kernel regression with respect to this. We're using kernel regression with the NTK to solve this linear problem where we've approximated the neural network by this first order Taylor series expansion. So if we show that that approximation is actually a very good approximation of a neural network that's super wide, then we're all good to go. And so the idea would be to show that a neural network, as the width grows larger and larger, is actually very close to a linear model. And so how do you show that a function is linear? Well, one way to do this, so how to show a function is linear? Well, the way to do it is that you just take the second derivative, in this case, the Hessian, and you show that the Hessian is very close to 0, while the first derivative, or the gradient, is constant. So here we will show the Hessian in 1D. This is like second derivative is close to 0, while the NTK, or this gradient, is constant. But remember, this is just not enough because we're actually training a neural network. What we actually have to show is that if the Hessian is close to 0 and the NTK remains constant, this property has to somehow hold throughout the entire training process. And so what I'll do now is outline the key steps in doing this. And this is exactly what the papers I've cited in the lecture notes do. And so here's the outline of the proof. Okay, so step 1, as network width goes to infinity, the Hessian of the network, this is now with respect to the weights, this approaches 0, while the NTK is constant. The second step is that actually, if the Hessian norm, so I should write it a bit different, the norm of the Hessian, and this is always this spectral norm, is uniformly small. And here I follow the notation from this paper. We'll say it's order epsilon. If this is small in a ball of radius r, then the change of the NTK in the ball is also small. So it's order epsilon times r. And then the last step, this is the clever step here. Whereas as the layer-wise widths go to infinity, gradient descent, when you train a neural network, will converge linearly, which is like fast convergence, to a solution inside this ball. So as width, again, goes to infinity, gradient descent will converge to a solution inside the ball. And this is gradient descent will linearly converge. And for those of you who are familiar with some optimization results, this is using the PEL or Polyak-Wojciechowski inequality. And it's based off this argument. So it's actually quite a simple argument to do this. But the details, there's still some technical details involved, apart from just the argument. And so these are the three steps. So the first thing is to show that the Hessian the norm of the Hessian gets smaller and smaller. So the model itself at initialization becomes very, very close to its linearization as the network width grows large. And then the second step is to show that in some ball around the initialization, the norm of the Hessian is still small. And then the third step, so the norm of the Hessian in this ball is still small, and the change of the NTK, if we were to find any solution in this ball, would still be extremely small. And then as width goes to infinity, we have to actually show that gradient descent converges to a solution inside this ball. So these are the three steps. What I wanted to do in this lecture is just cover step one. So let's just go through some simple example where, as the network width grows larger and larger, the norm of the Hessian becomes small, while the neural tangent kernel itself remains constant. Okay, so I've written this in the lecture notes as proposition 1. But again, we're just going to consider our standard neural network. But now, instead of working in d dimensions, we're going to work in 1 dimension. So we have a neural network that's given by f of x equals a phi bx. And here what I can do is just a is a 1 by k vector, and b is a just rk column vector. And so I'm going to let my neural network be denoted by a 1 over root k phi of bx for just some element-wise activation function. And now, instead of assuming the aij, bij's are standard normal, I'm just going to do something a little different. I'm going to assume these parameters are bounded. Then, for any bounded x, we have, so this is that the order of the Hessian, or sorry, order of the neural tangent kernel this is for any bounded x tilde, the order of the neural tangent kernel is just order 1. Whereas if I take the norm of the Hessian at either of these examples, it's going to be order 1 over root k. Okay. And in fact, I know this theorem is for this case where the variables a1i and bi are bounded. If you have them distributed according to some Gaussian distribution, then in this expectation, you'll actually have an O tilde, 1 over root k, which means you'll have some polylog factor coming into this norm of the Hessian. But let's not worry about that for this course. In this course, we're just going to consider, we just want to get some intuition about what's happening. So we'll just consider the case where these variables are bounded. Well, so the proof is actually just going to follow directly from this computation. So we already know that the kernel is going to be bounded, and it's going to have this order 1. This is just exactly following from the computation from before. But let's just first of all compute the gradients again. And the reason is that we are going to need these to compute the Hessian. So remember that the gradient here with respect to a1i, this is just 1 over root k phi of bi colon. Well, it would have been bi colon, but there's only one scalar here because x's are scalars. So it's just phi of bix. And then partial f with respect to partial bi, this is just going to be 1 over root k a1i phi prime of bix times x. And remember, this is just the computation that we did before for actually computing the neural tangent kernel. And now we can compute the Hessian terms, which remember, we're going to have to compute all these second order partial derivatives. So this, you see that there's no ai terms, a1i terms here. So this means that the second derivative with respect to this a1i, aij, this is just 0. And then similarly, if we do a1i partial bi, this is just 1 over root k. And I'm just doing these computations a bit fast because it's just a bit straightforward to compute these terms. But I encourage you all to work through it, especially in this simple case where you only have one-dimensional inputs. So similarly here, if we did partial derivative of bi with respect to bj for any I not equal to j, this would just be 0. And this is because you see that we don't have any bj terms appearing here. But if we take the second derivative with respect to partial bi and then bi again, well, this is just going to be 1 over root k a1i phi double prime bix x squared. Okay. So now the kernel, remember it was just the sum of these terms. So this is just going to be 1 over k summation I equals 1 to k phi of bix phi of bix tilde plus 1 over plus x times x tilde. These are just scalars now, so I don't need the transpose. And then it's again an average bix phi of bj, bix tilde a1i squared. Well, remember, we used a law of large numbers result. These are all some bounded terms. This is just exactly order 1. It's not vanishing as k grows large. And this is precisely because you have a 1 over k coming in here, and you're summing over k terms. So this is not going to vanish. This is going to be some function of k. This is going to be just a constant here. So it'll be independent of k. Okay. On the other hand, let's look at what the Hessian looks like. So the Hessian, this Hessian is going to be a big matrix. And in fact, if I grouped all the AI terms here, and then the BI terms here I'll erase this. So here I'll have my A1I terms and the BI terms. Well, you see that these partial derivatives here are just all 0. So I have a big block of zeros here. And now if I look at my partial derivatives with respect to A1I, BI, well, the i's better match. If the i's don't match, then I don't have a derivative. It would be 0. And so I have a diagonal matrix here. And this will all be 1 over root k, phi prime of b1x, x, all the way down to 1 over root k, phi prime of bkx, x. And remember, it better be symmetric. So I'll have the same matrix here. And now the question remains, what happens in this lower block on the bottom right? And remember, again, it's only going to be diagonal. So it's only going to have these diagonal terms. And these will be like 1 over root k, a1i, phi double prime, bix, x squared. Sorry, this will be b1 in the first coordinate. And then 1 over root k, a1k, phi double prime, bkx, x squared. Okay. So now what I want to do is I've actually computed the spectral norm of this matrix by exactly computing the eigenvalues. But there's a very simple argument we can do here. Let's just assume that the function that we're working with is like a ReLU, where if you ignore the point x equals 0, it's differentiable everywhere else, and it has a second derivative everywhere else, and that derivative is just 0. So when we have phi double prime, we can just replace all of these terms with a 0. So let's consider that case. So some function, so assume phi double prime equals 0. And so now we have this matrix that has this, it's very sparse, and it has this diagonal structure. And here, to even make it look a little nicer, I'll just put a big block of zeros here. And computing the eigenvalues of this matrix is quite easy, because we know that we can just take these one-hot vectors. So if I put a vector that looks like this, sorry, I should have said these, if these are these multi-hot vectors. So I have at most ever 2 ones in these. So in particular, if I look at the vector, which has a 1 in the first position, and then a 1 in the kth position. So this is position k, position 1, and zeros everywhere else. You'll see that this is an eigenvector with exactly eigenvalue 1 over root k, phi prime of bxx. So it'll have eigenvalue equal to this. On the other hand, if I plug in a negative into one of these, it'll have negative that value. And so in fact, what we're seeing is that the spectral norm of H, in this case, it's going to be a max over I and k of 1 over root k, phi prime, bix, x. And so because bi's are bounded, x's are bounded, this whole part is a bounded quantity. And so this max is just order 1 over root k. And so as k grows larger and larger, what this proposition says is that the spectral norm of the Hessian goes to 0, while the kernel is constant. And so in fact, at this initialization, your neural network is very well approximated by a linear function. In fact, it converges to a linear function as this width grows to infinity. And so this is the key idea around this proof. So we've at least done this one part. And I have the more general computation written out in the lecture notes. But what we're going to do in the homework is maybe analyze this case once more for a very simple network where instead of freezing the first layer and training the last layer, I would ask you to freeze the last layer and just train the first layer. And note that this is not equivalent to the neural network Gaussian process, because now I'm taking a neural network where I apply a nonlinearity, and that representation going before the nonlinearity is the thing that's changing. Okay, and now, given all of this analysis, so let's just summarize what we have so far. So we've defined, and computed the NTK. And now from the second step, the NTK kernel regression, solving kernel regression with the NTK is essentially equivalent to training infinitely wide neural networks with gradient descent. And now there's a few caveats I wanted to mention here that come from this analysis. So there's a couple of things that we need to address still. So points to address. So the first one is that, remember that in this linearization, what we actually did is we had this function and we took its first order approximation around some initial values. And thus far, what we did for the NTK is I just said, ignore this part here and this part here. And I said, just use this and solve kernel regression based off this feature map, this gradient feature map. So it turns out that if you do this and you compare against a finite width network, what you'll see is that there's a mismatch. So you'll see that you don't numerically exactly get what the finite width neural network was giving you. And this is because if you think about the actual training objective with this linearization, if we just substitute this into our loss, and we do f of xi tilde w, well, if I simplify this, this is just sum from I1 to n, yi, minus f of x at w naught plus gradient f of x at w naught transposed w minus w naught. Now, this w naught here, this extra difference, this is not such a big deal. Sorry, this should be a negative. This is not such a big deal because instead of initializing w equals 0 and solving this, what I would do is initialize with w equals w naught, and that will always get rid of this extra w naught term. So I can effectively assume that this w naught term is missing. But you see now that there's still a catch, and the catch is that we needed to transform the labels, the yi's, by the predictions of our neural network at initialization. And so what I will do is in the homework, you will explore this connection and actually see that going wider and wider will lead you to an exact match if you make this connection, if you make this small correction. And so numerically, you'll see like your neural network predictions versus the kernel regression predictions after this correction are like within 10 to the negative 8th of each other, or 10 to the negative 6th of each other. So we can very precisely match the behavior and predict the behavior of very wide neural networks. And this is, again, training all the layers. So this is a rather cool thing to do and check out that you can actually match this. Okay, so the second point I wanted to address, which was a little subtle for even the neural network Gaussian process, but what happens, so thus far we've considered neural networks where you only have scalar outputs. So what happens if now my yi's live in some c dimensions where c is greater than 1? So the trick here is that for fully connected networks, nothing changes. You just pretend that c equals 1. And what you do is you build your kernel. So I'll still build my n by n kernel just like I would when c equals 1. And then when you solve kernel regression, remember that you solve for these alphas. This is just alpha k hat equals y. And now my y, instead of y being a 1 by n matrix, and 1 by n vector, you just let y be a c by n matrix. And similarly, alpha is just going to be a C by N matrix. And this is it. So if you just do this, somehow solving kernel regression, you're solving these C-independent kernel regression problems, and you're good to go. And making this formal is a little bit tricky. You can think about it if you want to, but instead of the gradient, you'll have some Jacobian terms coming in for the feature map if you do this. And this is a little tricky to handle. But in general, for fully connected networks, is somehow coming from the independence of all the parameters in the last layer, we can get away with this trick and see that everything matches. You cannot do this for convolutional networks, unless you're considering convolutional networks which have a number of independent filters on the output. But we'll get into this in the next lecture. And so for fully connected, this is all you would need to do. And lastly, what I would want to mention is that there's some key points in the analysis of when the neural tangent kernel has this equivalence with training neural networks. So when does NTK sort of correspond to training neural nets? And in all of the neural networks we've studied so far, they have this key property that they do not have a nonlinearity on the output layer. And what do I mean by this? So all of our neural networks are of this form A5bx. They are not of the form phi of A5bx. And so this case here is bad. If you have this case, then you cannot use the linearization and get a good approximation for the neural network when you train it, even when it's super wide. And the reason is that when you actually compute the second derivative, you have to apply the chain rule to this extra nonlinearity on the output, and that will add some constant term to the Hessian, which will not necessarily vanish as k grows large. And so one needs to be very careful, and we always consider neural networks that look like this. And so what does this mean in practice? In practice, it means if you have a sigmoid or softmax activation on your neural network, you might not necessarily match the predictions of the neural network with the neural tangent kernel, even if you grow super, super wide. And so is this an issue in practice? Not really, because as you'll see that even linear networks with the square loss are very, very good classifiers. This is shown in several, this is shown in papers by, again, Misha Belkin's group. And even in this course, you can compare the performance of a classifier with a sigmoid activation at the end to that of the neural tangent kernel with no sigmoid, and you'll see that they're actually very close. Okay. So the last thing I wanted to do before concluding this lecture is again just talk about how do you actually do an empirical comparison between the neural tangent kernel and neural networks. So first of all, remember that nothing has changed for us. We're still using kernel regression. All we've done in this lecture is just define a new class of kernels given by the neural tangent kernel. So computationally, we use the same 3 kernel regression steps. The only difference is that now we have new kernels. Okay. So that's great. So now we can ask, how does training finite width neural nets compare to NTK? And in fact, it's not always the case that NTK is better than finite width neural networks. There's examples for convolutional nets where this is true, where this is not true. But in most cases, the NTK is very, very close to the performance of wide finite width neural networks. And usually it's sufficient enough to give a very strong baseline. And because it has the simplicity from the kernel regression framework, it's a very simple procedure to try out first to get something working. So we can again, in the lecture, what I do is again produce this plot. So this is just going to be our mean squared error. I pick some arbitrary regression function. In fact, I think I pick the true function that I want to approximate is something like x plus sine 10x, just in 1D. And I sample some number of points from this. And here what I'll do is I'll, again, do this double descent type plot, where I'll let k grow large. And I'll start from k equals 1 and make it k to 10 to the 24. And unlike the previous lecture, I'm now training all layers of the neural network. And so you'll actually see that the training loss, again, goes to 0. But then my test loss, you'll see it has, again, this nice pattern. In this case, in the lecture notes, what I do is a bit of early stopping, which actually you would have seen the peak here, but because training neural networks is an incredibly painful process, what you'll actually see is that with this early stopping step, this peak is sort of removed. You'll get something that looks like this. And you'll see that larger and larger models, so this is the early stop test loss. You'll see that just larger and larger models work better and better. And in fact, there's a sizable performance difference. So this I'll draw in red. And this is just the exact fit, the exact solution to kernel regression with the NTK. So this is the infinitely wide NTK. Okay. So here we'll see that the infinite width model actually does much better. And I should make a quick note because this early stopping is a bit of an annoying point. Ideally, what we would do is just train until your models perfectly fit the training data. And this is like get close to 10 to the negative 5 or 10 to the negative 6 error in training. The thing is that all of the models here, so let's say your interpolation threshold, so this is where your number of training samples is very close to your model capacity, so to K. What happens is that at this interpolation threshold, it's extremely difficult to get to very low loss. And this is optimization is just very hard because there's exactly one solution, and for some reason converging to this thing is incredibly painful to do in practice. And so what I typically do is I set an earlier loss threshold. So in this case, I set the threshold for training loss, anything less than 10 to the negative 2. I said was good enough. And so you'll get a clean figure that looks like this. And so it may be the case that even at the interpolation threshold, even though you could perfectly fit the data, we're incurring some hit on the training error. So we're not getting exactly 0, we're getting some non-zero value. But it's okay, because we'll still see that in generalization, this peak is basically removed and larger models do better. And this is sort of the emerging picture that we had anyway, of these big models doing better on this data set. And in the homework, you'll again have some chances to try and explore this. I've given some other functions, and I encourage you to try it out on realistic data sets like CFAR10 or ImageNet. Or there's small versions of ImageNet which work, or any speech data, or any other data sets like that. Okay. So I know there was a lot of new material in this lecture, but hopefully now you have at least some cursory understanding of where the neural tangent is coming from and how it connects to training very wide or infinitely wide neural networks. And in fact, we'll see that this connection holds in the case where you have networks of arbitrary depth and other layer structures. So things like convolutional networks. There's even papers on the neural tangent kernel for networks with attention. So some things like transformers or graph convolutional networks. So it's a very rich area. And the whole premise behind all of these computations is just how do we write in a systematic way this kernel? And how do we compute it as the width grows to infinity? And so if you know how to do that, you know how to compute these neural tangent kernels, you can use them in practice and you'll be good to go. And in the homework, I should say, even though we're doing all these derivations here manually, you won't need to do this. In fact, what you'll use is a very nice library by Google Brain. And this is called the Neural Tangents Library. And given almost any network architecture, and they consider a bunch of activation functions and layer structures, you just write out your neural network in the form, like maybe I use a linear layer, which would be like a fully connected layer, it's just a matrix. Then I can pick my activation, like ReLU, and I'll just write a list of layers that look like this. And I'll just ask the library to output what is the corresponding kernel function. And this will just give me the NTK for whatever architecture I picked. And this kernel function, if you feed in any two data points, it will just output you the NTK between those points. So it's an extremely convenient framework for abstracting away all of this computation. And so we'll actually get to try and use this in practice to see how well these NTKs work. So that's it for lecture 5. And I hope you all enjoyed the first introduction to the neural tangent kernel. And the next lecture, we'll go over these deeper neural tangent kernels and a convolutional neural tangent kernel. So see you in the next lecture.